Now, without further ado, let me introduce you to Professor John Hennessy, who is the chairman of Alphabet since 2018. So, John, I read that when you took over the role of president of Stanford, Walter Hewlett asked you to stop thinking about what's good for Stanford, but what should be good for society, for the humanity. With that, let's start with a very open question, which is, what do you think are the global challenges for humanity today?
Well, we certainly live in a challenging time, and when Walter asked me that question, I started thinking about what the role of universities would be in the world. You know, universities are often, we think of them as these ivory towers, right, where lots of people are talking within the ivory tower, but perhaps not always looking outside beyond the bounds of the campus. And if you're on the Stanford campus, you can understand why people might not want to look outside. But in any event, it was really an interesting question, because I started thinking about universities need to be much more engaged in finding the solutions to the really big societal problems. Because if universities don't engage, where are they going to come from? Where are the kinds of breakthroughs that maybe in an earlier time we got from places like Xerox PARC or Bell Labs or IBM Research, but today those don't exist. And while government's an important implementer, it's not the source of most of the breakthroughs. So today, I think you can see some of the movement that's really important. Obviously, the climate change, sustainable, I have grandchildren now. That problem has gone to the top of my list because I'm thinking about the world they're going to live in. That's obviously a big problem. Figuring out how we continue to improve the quality of life for the people that live in the lower half of the pyramid, mostly in the southern sector of our planet, that's a critical issue as well. Figuring out how we ensure that technology gets used for good. I mean, the AI revolution is exactly that. It's a revolution. After 50 years, 60 years, I mean, we finally got a breakthrough with machine learning of monumental size. Now the question is, how do we ensure that it does good in the world and gets used for lots of good, and we minimize the harms that we have? We've got to think about all these issues, I think, as we go forward.
And for the entrepreneurs who are listening, why is sustainability so hard, and how can technology help?
We do need technology. In the long term, technology will be the cornerstone of the solution. But we're not going to get there fast enough because the breakthroughs we need. I mean, look at battery progress. And I don't want you to just look at the price of batteries, because, of course, Elon's success with electrifying vehicles has driven the price down pretty fast. But energy density goes up between 5, 6, 7% a year. Not very much. We need a breakthrough. If I had a silver wand right now, I'd wave it, and we'd have a bulk, low-cost energy storage capability. Because if I had that technology, then I can dramatically accelerate the renewable energy solution, because I have a place to store that energy at night. I was giving a talk a couple of months ago, and I asked the audience, it was down at the Computer History Museum, so you can guess there are a lot of techies. I said, well, how many people have an electric vehicle? Now, how many people have an electric vehicle? Okay. How many people plug it in at night? And that sun is shining for you. It's just not shining locally in California at night. So there's a small problem there that we've got to solve this problem. You've got to have energy storage. So I think there's a good example of a technology. Fusion, you know, it's the technology 20 years from now, and it always has been. But if somebody makes the fusion breakthrough, and I think there are some big investments in some interesting new approaches that could lay the groundwork. But together with those technology innovations, we're going to have policy change. And my silver wand over policy change is carbon tax. Carbon tax. And it's not such a horrible thing. I think within 5 years, we can get CO2 sequestration down to a cost where the added cost of a gallon of gas might be $1. To be carbon neutral, you'd have a carbon neutral source. $1 a gallon, it was more than $1 a gallon a year ago. So it's an affordable, I'm not running on that as political, because I know where that would go. But you know, we're getting there. So technology together with policy is what's going to get us to this solution before we destroy the planet.
Although it sounds like it's also about unit economics to get to the right place.
It's absolutely. Because in the end, Tom Friedman once said, you've got to find a technology that solves the problem for a price that China is willing to pay. China is the largest consumer and burner of coal in the world. Coal is 4 times worse than natural gas. So we've got to get rid of coal. We should just outlaw coal globally, right? But obviously, while the United States has made a lot of progress in eliminating coal, it's been much harder in other parts of the world.
Let's move to computing a little bit. It would be strange not to talk about ChatGPT and all this advance of generative AI, which has really a lot of good applications, requires new type of computing, new type of connectivity. What are you most looking forward or excited about the next level of computing for this?
If you look at what happened with processors, we've kind of reached the point of diminishing returns in conventional general purpose processors. And by conventional general purpose processor, I mean a machine that can run a hunk of C code that is just sitting there native and doesn't have a lot of hints on how to do it efficiently or something, right? So it's got random pointers, it's got all the things that we're used to programming and that good programmers can do to get efficiency up. But we've kind of reached the end of the plateau, and if you think about it, it's really an energy efficiency. It's silicon efficiency to some extent, but energy efficiency is the big issue. And the reason is the techniques we use. Think about speculation, right? So all these machines speculate now, and I mean, if you look at a recent Intel processor, you know, it's got 100, maybe 150 instructions in flight at any given time. So it's speculated through 3, 4, 5, 6 branches, right? And what are the odds that it got each one of those 6 branches right? Because unless it got each one of them right, we're wasting time and energy. So speculation is kind of played out. It probably can't go a lot further. Even caches can't go a lot further. I mean, you build a multi-level cache and, you know, we were up to 4-level caches. I mean, it doesn't make any sense to go anymore at that point. So we're kind of playing that out. The interesting thing is, you might say, if you put aside the AI revolution, computers have gotten a lot faster and it's a little harder to find novel applications that really could be paid for or could justify much faster computers. But then you put AI into the mix and all of a sudden, for training and for inference and complicated things, we've got computationally demanding things. They behave very differently than traditional applications. They do a lot more streaming data access. They do a lot of linear algebra, both sparse and dense. So the machines need to be built very differently, and we need to move into this era of domain-specific computers, where we design a computer to do a class of problems, not one application, right? We know how to design a computer for one application, right? There's lots of them inside your cell phone. They do one thing, right? But we need to design computers which can do a domain of things like train or like inference kinds of problems and make them very efficient. And we do that by using a variety of different techniques, right? You don't need 32 bits for a lot of things. You don't need 64 bits. IEEE is way overkill for most of these kinds of problems, right? But you've got a lot of parallelism, and you have to exploit that efficiently. And you've got a lot of streaming data accesses, so caches may not be the smartest thing anymore. But the programmers know a lot more. And so by combining both new programming systems, things like TensorFlow or CUDA, that are designed to program in that environment, together with new architectures. I mean, the levels of performance, it's interesting now when you think about the fastest machines in the world are now being used to train these large language models, not to do these giant scientific calculations anymore. They have some big machines, but the fastest machines in the world are now being used to train large language models.
You talked about good programmers. It doesn't feel like we will need good programmers anymore.
Yeah, so I think don't trust the code you get out of a large language model. Dan Bonnet, my colleague at Stanford, has written this paper that basically says, well, the problem with large language models as code generators is they don't always get it right. But we believe they got it right, and they believe they got it right. So basically, the code's wrong. Nobody looks carefully at it, because everybody knows that reading somebody else's code is really hard anyway. So kinds of things slip through. And one of the things that Dan documented in this paper is that with respect to security holes, that's where it's possibly most dangerous, and where we basically need a programmer. Now, that doesn't mean simple kinds of things like a UI for something that's going to be easy kind of stuff. I think you will get decent code for those kinds of things.
I already can see a joke where a programmer will say, oh, we have a security problem with AI, and then someone will say, oh, just call another AI to fix it.
Yeah.
I ask you about what you're excited about computing. How about connectivity?
So I think we've seen lots of progress in connectivity. We're pushing the edge of optical, for example, getting a lot closer. I think things which 10 years ago we never would have thought of converting to optical to connect, today we would. And inter-rack kinds of things, very short haul things, are now going to go to optical to get the bandwidth up, and we'll pay the cost of electro to optical conversion. That's an area where if we had a real technology breakthrough that did some kind of hybrid solution, so that we didn't have to cross a package boundary to go from electrical to optical, we could really get significant enhancements in terms of performance per power. Clearly, we've become this wireless world, and it's completely happened, and I think we'll see continued progress there, although there are certainly challenges in making further progress on that in terms of distance issues and coverage and all kinds of things like that that we're going to wrestle with. But I wouldn't, just as the Wi-Fi generation was a real breakthrough in making that technology work in CMOS at reasonable power levels, I wouldn't put it past another breakthrough coming through and somebody really making a big jump in terms of mobile connectivity.
So before I take questions from the audience, both in person and online, I'll ask a fun question. If it's not 2023, when do you think singularity is happening?
So there's two parts to this question, or two parts of the answer. One is, when will large language models pass the Turing test? I think the answer is they pass the Turing test today for people who aren't experts. They pass the Turing test today. There's no way somebody who's a basic computer user couldn't be equally fooled by a large language model. So I think we're already at that level. The singularity problem applies that it's some sort of artificial general intelligence kind of level. Okay, so here's what I'd say. I used to think 20 to 40 years. I cut that in half. But some of my colleagues would say within 5 years that we'll get there. But I think within 10, we'll get there where even an expert across multiple disciplines couldn't tell whether they were dealing with a computer or a person. Now, this isn't how the computer doesn't start replicating itself and unplugging humans and replacing them. But I think in terms of capability, multimodal, across different things, I think we'll be there.
And actually, if it's domain-specific, it's probably 1 to 2 years away.
Yeah, domain-specific, where there, I mean, even mathematics or code. I mean, mathematics, I think these new systems, Bard can explain mathematics to the level of somebody who's a graduate level researcher in mathematics. And that's pretty good, since that's probably the 98th percentile of human cognition in terms of math.
Who wants to ask? Jeff.
It wasn't a secret that Google, had built some of these large language models several years ago. It just took a while. My question is, what's next? We deal well with images. Now we're dealing with natural language processing and language and voice. Where do you think the next big bang is going to be? I have my own opinions, but I'm kind of curious. Like, the seeds must have already been planted now. Like, the AI frameworks continue to evolve, and we've now got a few good ones. What do you think is the next big breakthrough?
That's a good question. I think GPT-4 is the kind of first cut at a multimodal model. So, I mean, a model that will do natural language, but also have in-depth domain information. It can discuss, for example, a mathematical proof. Not just show you the proof that it got from somewhere trained, but actually explain the proof in natural language. Explain a piece of code. So one of the things that the guys at DeepMind are trying to do is not only write code, but you can then ask, why did you write this piece of code this way, and get an explanation of it. I think video, we've already seen some deep fakes that are really worrisome, right? Not full video, well, almost full video. Let's say a head-on zoom with lips moving, the voice matches the voice of somebody, but it's not that person. That's already happened, and they're trying to use it to do terrible things in the world. We've got some issues there. One that's going to be really important is one that one of our scholars at Stanford worked on. It's called Detect GPT. So I think we're going to have tools that detect whether or not something is a deep fake or not, and really deal with that. You know, it's a little hard to predict because the large language models have emergent behavior. Not emergent in that they're starting to come alive in some way, but emergent behavior in that they do things that the people who built them wouldn't have guessed ahead of time. They're more capable than the people would have guessed. And I've never seen that in computer science. Never in my 50 plus years and 60 plus years in the field.
We saw a glimpse of this with Go, where some of the world champions were surprised by some moves.
Yeah. I mean, it's AlphaGo. It starts out, it makes this move that no Go champion in the world would ever make. And so as he said, Sudoku said it, and he said, it played a creative game. Well, when you talk about computers being creative, that's a kind of different thing.
Creative and elegant.
And elegant, yeah.
Yes, G?
Hi, Gayatri or G with Hitachi Ventures. I just looked up on Bard, and it said it takes about, or GPT model emits about the same amount of carbon dioxide as it does as a car that drives for 100,000 miles, right? So you talked about reaching singularity in like 10 years or so. What is your view on sustainable AI, and can we get there without burning the, planet we live on?
Yeah, so first of all, you have to separate out training from inference. You're not going to train these models every day. You're just not going to do it. And that has some implications for how we merge large language models with things like search so that you can get up-to-date information, because you're not going to be able to train the model every day. You can do some fine-tuning to add more recent news events, for example, in there, but we're going to have to find a better way to kind of merge these technologies. I think we're going to more attention to how we're going to, what hardware we're going to use to train these things, train them more efficiently, get green sources for energy so that they're not generating CO2 when they're being trained. Inference is a much easier problem, much smaller quantization. You can use smaller, very small. I mean, it's amazing the things people have done with inference using only single bits for weights. I mean, so there's a lot to be done there that will be really important, and that will have to be important because the edge devices are not going to have large power supplies. They may even be on battery, but they're where you have to do inference, right? So we're going to have to figure out how to merge these things along and find effective ways to solve the problems.
Okay, one in the middle.
My question is, where do you see as the value accretion from a startup compared to a large company with a lot of data? For instance, Midjourney with 11 full-time employees. On the other token, from AI infrastructure company to Copilot, vertical application side. What's your view on where the value land?
You look at history of Silicon Valley and what's happened over the last 40, 50 years, and startups have always played a key role in bringing new technologies which perhaps the established players were not willing to invest in and use initially. along and make those technologies incredibly successful. And you just look at history over history. Well, shouldn't Yahoo have figured out that there was a better way to do search and Google never should have been created? Shouldn't Google have figured out that social media was going to take off and Facebook never been created? But that's not the way the Valley works. The Valley kind of is this constant retry of stuff. And the other thing I'd observe about it is there's basically big wave effect that occurs periodically when some new technology, mobility came along, right? And the idea you could get mobility. You know, when we started Atheros, half the VCs turned us down. They said, "Oh, you're technically too ambitious. It's not time yet. Come back in 5 years." So that happens periodically, and what the entrepreneurs do, in my impression, particularly entrepreneurs are taking a new technology out, not just building a niche product, but it's a new. They see the glass as half full. Everybody else sees it as half empty. And that's the difference. And the entrepreneurs are going to work as hard as they can to try to fill the rest of that glass. And that's what's going to make the difference. And I think the one thing you learn having been in Silicon Valley is don't ever get comfortable. Because when you get comfortable, the new startup is going to come along and eat your lunch.
John, I had one more question, but I have to finish with this. This was too good. Thank you, John. It was amazing.
Thank you. Thank you all.